We are batch A14 from the Department of CSE AML A section. Our project is titled Real-Time Multimodal Human-Robot Interaction, a vision speech conversational framework for attendance automation. We are a team of 4: L. Karthik, K. Vishnuvardhan, G. Rahul Reddy and J. Raviteja. This project is developed under the guidance of Dr. K. Shivakrishna Sir, Associate Professor. We will be covering these sections in this presentation. In most educational institutions, attendance tracking and student-teacher interaction remain two major challenges. Attendance is still marked manually, which consumes valuable class time and is prone to errors. More importantly, students hesitate to interact with faculty due to fear of judgment and social pressure. This prevents them from clarifying doubts, seeking guidance, and growing academically. To address both these problems, we propose a humanoid robot integrated with AI, computer vision, and speech recognition that automates attendance and provides students with comfortable, judgment-free interface for real-time interaction. Our system is an AI-powered humanoid robot designed to modernize classroom management. It replaces manual attendance with automated face recognition and replaces the communication gap between students and teacher with an intelligent conversation interface. The robot integrates computer vision, speech recognition, and machine learning to deliver accurate attendance marking with real-time interaction, enhancing institutions' efficiency and student engagement simultaneously. Now coming to the objectives of our project. Our project is built around 4 objectives. First one is to automate attendance using AI-based face recognition, and second objective is to enable real-time interaction between students and robot as a judgment-free alternative to direct faculty communication. Third objective is to reduce manual workload on teachers and save classroom time. Fourth objective is to combine computer vision, speech recognition and machine learning into one unified robotic system. Coming to the literature survey of our project, we have reviewed over 25 research papers related to face recognition, attendance automation, conversational AI, and human-robot interaction. The key finding from our review was the existing system works address these problems separately. There is no prior system combines attendance automation and conversational interaction into a single robotic framework. That gap is what our project fills. Coming to the existing systems of our project, three types of systems currently exist. They are manual attendance, biometric or RFID, and online LMS portals. Manual attendance is time consuming, error prone, and allows proxy marking. Biometric and RFID systems require physical contact, high maintenance cost, and offers no flexibility. Online LMS portals lack automation, have no AI-based verification, and do not support real-time student-faculty interaction. None of these systems address the communication barrier between students and teachers. Our proposed system is a humanoid robot that marks attendance through face recognition and enables voice-based interaction with students. The advantages are it is accurate and proxy-free, it saves classroom time, it reduces teacher workload, and most importantly, it gives students a safe and approachable interface to interact without hesitation or fear of judgment. The system is secured, automated, and fully operational on edge hardware. In our project for face recognition, we collected 500 to 800 facial images covering varied lighting conditions, angles, and expressions to ensure robustness in classroom environments. For speech recognition, we used over 100 audio clips to train the intent classification and response module. The dataset is designed to reflect real-world conditions, not just controlled lab settings. On the hardware side, we are using the NVIDIA Jetson Orin Nano 8GB for edge AI processing, an RGB depth camera for depth-aware face detection, a microphone and speaker for voice interaction, and a robotic base for mobility. On the software side, the system runs on Ubuntu with ROS, programmed on Python language. The core libraries include YOLO V8 for face detection, TensorFlow for deep learning, WOSC for offline speech recognition, and LiveKit for real-time communication. Firebase is used as the database. This diagram shows the complete hardware and software architecture of our system. The camera and microphone feed into parallel AI pipelines, vision and speech, which converge at the processing layer running on the Jetson. The output is then routed to one of three actions: attendance marked to Firebase, a spoken response through the speaker, or a navigation command to the robotic base. The architecture is modular, meaning each component can be updated or replaced independently. Coming to the methodology of our project, the algorithm works as follows. The camera captures a face frame. MTCNN detects the face region. FaceNet converts it into a 128-dimensional embedding. Then simultaneously, audio is captured and converted into text using the ASR module. An intent classifier then determines the user's intent, whether it's attendance, query, or navigation. If the intent is attendance, the embedding is compared to the database using cosine similarity and a liveness check is performed. If both pass, attendance is marked. If the intent is a query, a response is generated and spoken. If it is a navigation, the target location is extracted and the robot moves accordingly. We have used two mathematical models to power the core of our system. Arc phase matching is used for attendance verification. It maximizes the angular margin between different phase identities, making recognition highly accurate even under varying conditions. Intent classification uses a probability-based model to determine from speech whether the user wants to mark attendance, ask the question, or request navigation. Both models are integrated into the real-time pipeline running on the Jetson Nano. These are the step-by-step implementation of our algorithm. Coming to the implementation part of our project, this slide shows the voice module implementation. The voice module.py file handles the complete voice integration pipeline. Figure 2 shows the initialization of audio parameters, channel configuration, frame size, and baud settings. Figure 3 shows the conversational initialization function, which is the entry point of every humanoid robot dialogue session. Coming to the results of our project, Figure 4 shows the output of a live conversation between a human and the robot. The robot correctly understood the input and processed the intent and delivered a relevant verbal response in real time. This is a working demonstration. The figure 5 shows the text-to-speech latency distribution. The distribution is consistent and within real-time thresholds, confirming that the robot's spoken response are delivered without noticeable delay during the interaction. In this slide, the figure 6 shows the accuracy comparison across multiple speech-to-text models. We evaluated several models and implemented an automatic fallback mechanism. If the primary model fails or drops in performance, the system automatically switches to the next available model without any interruption to the user. This graph shows the performance of each model and validates why the fallback order was chosen the way. In this slide, the figure 7 shows the LM response latency distribution. The results confirm that the conversational AI module responds within acceptable real-time limits, making it suitable for deployment in an actual classroom environment. In this slide, the figure 8 shows the voice listener node running on ROS 2. This confirms that the voice model is not a standalone script. It is a fully integrated node within the robotics middleware, publishing and subscribing to the ROS communication network in real time. In this slide, the figure 9 shows the SLAM mapping output in vector space. Simultaneous localization and mapping allows the robot to build a real-time map of its environment and navigate autonomously. This confirms that the navigation module is functional and the robot can localize itself and plan paths without human guidance. To conclude our project, our system automates attendance accurately using face recognition, eliminates proxy marking, and provides students with a comfortable judgment-free conversational interface that removes the communication bridge between faculty and students. The system is robust, edge deployable, and includes an automatic fallback mechanism for reliability. It is a practical solution for building smarter and more inclusive educational environments. We have filed the following patent document for our system. This is the IEEE conference paper we have submitted for our research project. These are the references for our project from IEEE conferences. It covers CNN-based attendance systems, deep learning for fraud management in education, and facial recognition for identity verification, and have helped us in developing our project. We would like to express our sincere gratitude to our guide Dr. K. Shivakrishna sir and our HOD Dr. K. Sai Prasad sir for supporting us in this project. The following is the working demonstration of our project. Thank you.
Hello, I am Rebucked, your college robot assistant. How can I help you?
Hi, how are you?
I'm doing great. Thanks for asking. Have a wonderful day ahead.
What is your purpose?
I'm here to help students and staff with college info, attendance, counseling, and support teachers to make things easier.